Hi, so it's a
I've done
pleasure
very
to have,
fine.
yeah, so it's a pleasure to have Clement here today, who will be telling us about higher categorical symmetries engaging on the lattice. Uh, Please take it away, Clement.
Thank you. Thank you for having me and giving me the opportunity to talk today. And so today I will be telling you about a certain type of generalized symmetries, a fairly general type of generalized symmetries that are often referred to as higher categorical symmetries. And these have been under intense scrutiny in the past 2 years in particular. And there has been like several talks in this seminar series on this very topic. But the difference is that today I want to tell you about a manifestation of these higher categorical symmetries in the discrete setting, so for lattice models. So the idea is to show, to construct explicitly on the lattice the symmetry operators that correspond to these higher categorical symmetries, but also show that very simple spin models that are relevant in condensed matter theory, for instance, turn out to have very exotic symmetry structures. So what started this whole business was to pay attention to the fact that symmetry operators are topological operators. And this topological invariance of symmetry operators is nowadays taken as the defining feature. And this has led to statements along the line that quantum theories assign topological operators to global symmetries. And this gives you an intrinsic way of thinking about symmetries without referring to a specific Lagrangian or specific Hamiltonian. But also it suggests many generalizations of the usual concept of symmetry. And so in particular, you can consider symmetries with respect to higher codimensional symmetry operators. But also the fact that symmetry operators are topological does not specify that the fusion rules or the way you compose them has to be governed by some multiplication rule of a group. And in particular, you can have non-invertible symmetry operators, and then you can combine these various generalizations. So several specific generalizations of this type have been studied in detail in the past years. In particular, you can consider theories that just have what we call a higher form symmetry. So you have a symmetry, but with respect to higher conventional symmetry operators, in that case, the composition of these operators is still governed by a group, which has to be abelian in that case. You can also combine several higher form symmetries. So let's say in 2+1 dimension, you could have symmetry operators that are surface-like, but also line-like symmetry operators. And in the case where they don't commute with one another, for instance, the surfaces acting on the lines, then you would have what we call a higher group symmetry. And if you gauge, provided that this is non-anomalous such symmetry, you have what we call a higher gauge theory. Now, by restricting to the one-dimensional setting, in which case these higher form, higher group symmetries are not really relevant, what you can do is to relax the invertibility of ordinary symmetries, and you can have these non-invertible symmetry operators, often referred to the resulting symmetries as categorical symmetries. And these turn out to be very common in 1+1 dimension, related in particular to rational conformal field theory. And there are fairly systematic ways of writing lattice models that commute with such non-invertible symmetry operators. These are usually referred to as anionic chains. And so today, my focus, and which has been the focus of many other groups, is to essentially combine these ideas and to find examples of symmetry structures that are of the higher group style with like different operators of different codimensions, but that are possibly non-invertible. And the resulting general type of symmetry is referred to as higher categorical symmetries. So although these higher categorical symmetries may sound very exotic, and generally speaking, these general symmetries may sound exotic, it turns out that they are a fairly simple mechanism that produce such general symmetries. In particular, it has been quite understood that some type of gauging or generalized gauging procedure of an ordinary symmetry will yield some generalized symmetry. In particular, for instance, in D dimension, you have zero form symmetry with respect to a group that could be non-abelian. If you gauge this group, then you have a D minus form symmetry, but the symmetry operators are labeled by representations of the group rather than group elements. So this is basically the statement that the Wilson lines, the theory generate this minus form symmetry. And I would like to highlight a few papers which follow this guideline of creating or generating new symmetries by gauging ordinary symmetries. But these papers, they went further in the analysis of the resulting structure. In particular, they emphasize the fact that we don't just have a higher form symmetry of this type, but there are other symmetries. And when you take all these symmetries into account, you find that the symmetry structures are associated with the higher representations of higher groups. And so in this talk, I want to, the story I want to tell you is very much along these lines. It's about gauging ordinary symmetries and revealing that the resulting models have symmetry structures associated with higher representations of higher group. But I want to do that on the lattice. And so the first thing we need to answer is how to actually do the gauging in practice, given a specific Hamiltonian in that case. And the reason why I'm emphasizing that question is because I mentioned at the very beginning that it was possible to think of symmetries in a very intrinsic way without referring to a specific theory. That implies in particular that it's possible to also study the consequences of gauging a theory, of gauging a symmetry, without referring to a specific theory. Using more formal arguments, it is possible to compute what is going to be the resulting symmetry structure, even if you don't have a specific theory in mind. So the question I want to address is how you actually do it if you have a specific theory in mind. And although there is like kind of a canonical procedure to gauge in principle, it's not that easy to do in practice. And I want to present a framework that makes this a lot easier. And the second question is, so to actually compute what are the resulting symmetries, once we've done that gauging, by explicitly constructing the corresponding symmetry operators and check that they do commute with the Hamiltonian that we have. So this presentation is based on this work that we've done with a proof theory within the audience. And it's very much inspired by other works that I've been doing with Lawrence Lutens, Gerhard Ortiz, and Frank Strate in the one-dimensional setting, where we derived a systematic way of studying dualities in one-dimensional models that have non-invertible symmetries. Okay, so how does such a higher categorical symmetry would look like in general in 2+1 dimension? And 2+1 dimension will be the focus of this talk. So loosely speaking, a higher categorical symmetry in 2+1 dimension consists of topological surface operators, which you can compose. But in general, the result of such composition will not be a simple surface operator. It will decompose into a sum of simple operators. So this is the statement that these surfaces are non-invertible. For every surface, we can have line operators living on the surface. These are topological. You can move them freely as long as they stay within the surface. And then again, you can compose them. And typically, the result of such composition will not be a simple line. It will decompose into a sum of some simple ones. So this, you should think of, for instance, these lines as being Wilson lines labeled by representations of possibly a non-abelian group. In that case, the composition would be given by the tensor product of these representations. And as we know, the tensor product of irreducible representations of a non-abelian group decompose into irreducible ones. Naturally, we have a notion of trivial identity surface operator. This trivial operator can also have lines, topological lines on them, in which case this would generate some higher form symmetry. But also, and this is something a bit exotic, it is possible to define line operators between a non-trivial surface operator and the trivial one. In other words, it's possible to define a surface symmetry operator with open support, something that you cannot do, for instance, in one dimension. And so when you put all this data together with some consistency conditions for these various ways you can compose these operators, you get the structure of a fusion to category. So let me give you a very simple example right away before telling you a bit more about the general story. So this is really the simplest example you can think of on the lattice, which is the transverse field Ising model. So briefly, this model, here for sake of concreteness, I'm going to define it on the triangular lattice with periodic boundary conditions. So a triangulation of a torus, but you could do it on any triangulation of any manifold. And the degrees of freedom, they are located at vertices. And you can think of them as qubit degrees of freedom. Or rather, you can think of, you have a Z2 matter field at the vertices of your graph. These degrees of freedom, they are governed by this lattice Hamiltonian, where here the sigma matrices are the Pauli matrices, so sigma z, sigma x. So you have a nearest neighbor interaction for every edge, and then you have the transverse field. This model obviously has a Z2 symmetry, an ordinary zero-form Z2 symmetry, which is generated by the simultaneous action with Pauli X operators on every side. This is the only symmetry of this model. So it's just a Z2 symmetry, an ordinary symmetry, which in the category theoretical language, we would refer to as a 2-vec Z2 symmetry, which is the fusion to category of a Z2 graded 2 vector spaces, but it's fine to think of it as just a Z2 symmetry. Now, let us gauge this model, because I mentioned at the beginning that gauging was a way of getting more exotic symmetry structures. So here I'm going to follow a canonical approach of gauging, and later on I will tell you how we actually do it more generally for more complicated models. So the idea to gauge the symmetry is that first you need to couple the theory with the gauge field, a Z2 gauge field, which concretely here means assigning a qubit or Z2 degrees of freedom to the edges of your graph. And the fact that this must define a gauge field, it means that you have some kinematical constraint that we impose. And this kinematical constraint, this is a statement that the product of these Z2 group variables on every triangle have to be the identity. In other words, they have to be the states, the physical states have to be in the +1 eigenspace of these operators. Now we make the symmetry local. We define these Gar's constraints, which is a local version of the Z2 symmetry. And we can check that these Gar's constraints, they commute, and therefore we can impose them, all of them kinematically at every vertex. Now we want the Hamiltonian to commute with this local version of the Z2 symmetry. Now, obviously the initial Hamiltonian didn't, so we have to modify it a little bit so that it will commute with these Gar's constraints. And we do that by what we call minimal coupling, is that we add a minimal number of terms to the Hamiltonian in such a way that it commutes. So in that case, you can do it by just adding this Pauli Z acting on the edge in between these other two Pauli Z's. And then you can check that it does commute with all the Gar's constraints. So that's essentially the gauging. Now, usually we don't quite stop there. Is that what we want is to work in a basis of states that manifestly solve the Gar's constraints. And one way to do that is that you can perform a change of basis, such a way that the Gar's constraint just become this on-site action with Pauli X operator, at which points the matter degrees of freedom at the vertices essentially become classical. So you can forget about them. And then you end up with applying this unitary with this Hamiltonian. So we have an on-site sigma z, and then we have Pauli X operators acting on the edges surrounding a given vertex. And let me emphasize again that the Hilbert space is spine by space states of this form, which are assigned in that case. So it's really a spine by gauge fields. So it assigns Z2 degrees of freedom to the edges in such a way that they satisfy the kinematical constraints written above. In other words, every such assignment, you can think of it as a one cocycle valued in Z2. Okay, so that's the Hamiltonian. And here I give you, just to fix ideas, I give you a graphical representation of this vertex operator. So this is the second operator in the Hamiltonian. You see, you act with Pauli X operators on all the edges surrounding a given vertex. Now, what is the symmetry? The symmetry structure of this model, when one symmetry is a one-form Z2 symmetry, which is generated by products of Pauli Z operators along any contractible or non-contractible cycle of your graph. So indeed, so for the triangles, for every contractible cycle, this just follows from the kinematical constraints that we had at the beginning. But also you can see that if you take a chain of Pauli Z's like that along a non-contractible cycle, it will commute with the Hamiltonian because you will always use an even number of times the commutation relation with sigma Z and sigma X. And let me emphasize that rather than thinking of this as a one-form Z2 symmetry, I rather want to think of it as a rep Z2 symmetry, in the sense that I want to think of these operators as being labeled by representations of Z2 rather than Z2 group elements. And this translates into the fact that here the symmetry is with respect to Pauli Z operators, while the original Z2 symmetry was in terms of Pauli X operators. So this is in the very simple setting of a Z2 symmetry, but more generally, and I will present a non-abelian example later, we have this statement that in 2 plus 1D, gauging a zero-form symmetry would give you a one-form rep G symmetry. So that's one symmetry, but that's not the end of the story. It turns out that you have a lot more things in this symmetry structure, and in particular, you have a non-invertible topological surface. Now, there are several ways of defining this topological surface. I have here several definitions. One way is you can think of the action. So this is an operator that acts diagonally in our basis. And it acts essentially by coupling, by coupling it with a pure Z2 gauge theory. So let me clarify what I mean. If you look at the expression in the middle here, if you forget about the G, if you just have this big at the end, that's basically that's the action of a Z2, a BF theory or untwisted digraph return theory, depending on how you want to think about it. And the idea is that it's coupled to the background gauge field. Now, what you can do is that you can integrate over B, and then you're left with this Kronecker delta here. And the way to think of this expression is, one way to think about it is as follows. Is we assign, if you want, virtual Z2 degrees of freedom to the vertices of your system. And they have to satisfy a constraint, which is that if you take the sum modulo 2 of these virtual degrees of freedom at the endpoints of a given edge, it must be equal to the value of the gauge field at that edge. And then you sum over all possible configurations like that of virtual degrees of freedom at the vertices that satisfy these constraints. Now, what it does at the end of the day is that this operation projects onto the singlet sector of the Z2 one-form symmetry. This is at the end of the day, the action of this operator. Now, it does commute with the Hamiltonian. Easiest way to see it is just because it follows from the gauge invariance of the pure Z2 gauge theory. A more kind of a bit more concrete hands-on way of seeing it, which is represented by a bit heuristically by these diagrams, is the idea that if you have, so you have a gauge field, right, a given configuration, and then you have a configuration of these virtual degrees of freedom at the vertices that satisfy these constraints encoded in this Kronecker delta. Then when you act with the Hamiltonian, in particular with the vertex terms of the Hamiltonian, it's going to shift by one the value, you know, on the gauge field. At which point the previous configuration of degrees of freedom at the vertices is not valid anymore, but an easy way to have a valid one is just to shift the one in that vertex by one. And then just by changing the summation variables, you see that your operator is left unchanged. So at the end of the day, it's really immediate. It's just a change of summation variable. Now, these operators, I said they were non-invertible. And in order to check that, we have to compute their fusion rules. In that case, the fusion rules, well, how does it work? Well, if you act twice with the operator, you know, you're going to sum twice over this virtual degrees of freedom at the vertices. But these two sets of degrees of freedom, they have to satisfy exactly the same constraints. And this imposes that either N1 and N2, these Z2 configurations, they are the same everywhere, or they everywhere differ by one. So you have a split of the resulting operator into two Z2 orbits. And basically the result is that when you act twice with this operator, you find an operator that decomposes in 2 copies of the initial operator, which is obviously a non-invertible fusion groups.
Is this non-invertible surface correspond to this string which carry spontaneous Z2 symmetry breaking state of this Z2 gauge charge?
So I think so. This is the same idea. I think the interpretation is a bit different. I think the string you're thinking about is more as a charge rather than a symmetry, a generator of the symmetry.
Oh, I see.
But it's the same like category. I mean, mathematically, they correspond to exactly the same object. It's a non-trivial object in a 2-rep Z2. So this is the same.
I see.
Yeah.
Okay, so you can view that surface as a symmetry transformation or view this as a charge. Okay, yeah, thank you.
Yeah, so actually maybe this, so what I'm going to say just now should shed light on this.
Yeah,
there is another way of thinking of this operator as a condensation defect. And the idea, so again, there are several ways of looking at it. One way is to say that this operator is the same thing as summing over all possible line operators, so the ones that generate the Z2 one-form symmetry. You sum over all possible lines, and this is the same as, this realizes the same operator. You can see it explicitly by manipulating either this partition function that we had, or by just, you take this Pauli Z operator and you say you sum over all possible loops of sigma Z operators, then you can put, and it has indeed the effect of projecting onto the singlet sector of the one-form symmetry. So I guess in the context of what Shagan was saying is that the corresponding charge would be like a gas, a 1D gas of E charges. So something we can do as well is define these operators on an open support. In that case, it's very easy. We just restrict to a subcomplex. So we restrict the partition function of the pure Z2 gauge theory to a subcomplex. And one configuration that's interesting in particular is to define it on a thin strip like this on a manifold. And when you take the strip to be as thin as possible, you can interpret this operator as basically performing the composition of the line operators at the two associated with the two boundary components of this strip. Now, by looking at the definition we have above, this idea that is, in the end, this strip is just like summing over all possible lines that we can define on this strip. In that case, there are just two lines. There is a trivial one, and there is this line of sigmas. So what it means that if you look at this strip from far away, at the end of the day, this is just a line operator on the trivial surface charge, and this line operator is the sum of the trivial line plus the non-trivial one. And so putting all of this together, as well as a few other things, you obtain the actual symmetry structure of this Z2 gauge theory, which we obtain by dualizing or by gauging the Z2 symmetry of the Ising model. And this symmetry structure is often referred to as the fusion 2 category of 2 representations of Z2. And I will say a few words about what this means more mathematically later. So what is the general story? So the take-home message, which is basically what we are able to do, is that given a generic symmetric G-symmetric Hamiltonian, so with an ordinary symmetry, we can perform the gauging of any of its subsymmetry. We can actually do the twisted gauging associated with some choice of 3 cocycle. We can find so more in a more systematic way than what we did specifically for the Ising model, the symmetry operators that commute with this Hamiltonian and the corresponding fusion 2 category they organize into. And also, we can also realize on the lattice, actually, the operators that perform the gauging in the first place, or if you want to think of it as a duality relation. So how do we do that? But this relies on the fact that there is a systematic way of constructing lattice models that commute with higher categorical symmetries. So specifically for the examples, in the context of this presentation, what we can do is the following. Given a finite group G, which rather we should we would, in the fusion to category context, would be, we think of it as a G graded of two vector space of two vector spaces. We can construct a family of Hamiltonian, which depend on two things. First, this Hamiltonian depend on some choice of algebra of local operators, which will dictate the actual physics of the Hamiltonian. And also, they depend on something else, which is a choice of what we call a module to category over this fusion to category 2vec G. Now, this choice of module to category, physically what it encodes, it encodes a choice of gap boundary condition for the pure 2+1D G gauge theory. And we understand the classification of these objects, and in particular, the indecomposable ones, they depend on the choice of subgroup and the choice of a cohomology class. Now, these Hamiltonians, by constructions, because of the way we define them, we know what are the resulting symmetry structure. And the symmetry structure, the fusion to category, are referred to as the Morita dual of these 2vec G with respect to the choice of boundary condition. And this is something that we can compute, completely formally as separately. It's a well-defined object that we can compute. So in particular, there is a choice of gap boundary condition you can always make, which is a Dirichlet boundary condition, which mathematically means choosing 2vec G as a module over itself. And in that case, the resulting model will have a G symmetry. Okay, so what is the point of this? The point of this is to say that, let's say you construct a Hamiltonian choosing the Dirichlet boundary condition, and it depends in particular in the choice of local algebra of local operators. And now we keep everything fixed, but we changed the implicit choice of boundary condition that we make, or we change the Dirichlet boundary condition by another one. And doing that amounts to actually gauge the model. And to gauge, we gauge the subgroup, the subsymmetry associated with the subgroup that enters the definition of this boundary condition. Now, before saying more concretely how this works, let me briefly mention that there is another way of doing something similar, which is completely equivalent, is instead of using this language of module to categories, to use the language of separable algebra objects in the input category. And these are equivalent, invoking, and I'm mentioning it because this is an approach that has been pursued by several people in this community. And the equivalence relies on the fact that the module to category over a fusion to category in general is equivalent to a category of modules over the corresponding separable algebra. So this statement is a categorification of a well-known statement that is due to Ostrich, and this categorification was mainly studied by Clement Delcamp. Okay, so how does it work more concretely? The statement, the kind of take-home message is that if you have a way of writing a model that sort of explicitly depends on a choice of module to category over 2vec G, if you change this module to category, it amounts, the resulting model is related to the initial one by some twisted gauging. So how does it look like? Well, the Hamiltonian, okay, is just a sum of local operators that act on some neighborhoods of vertices of your triangulation. And these local operators can come in several flavors, here just labeled by N. Now, how does these local operators look like? There is first kind of a universal part. These are just complex coefficients. And these complex coefficients, they essentially dictate what is going to be the algebra of local operators of the model. This is completely independent from the choice of boundary condition, of the choice of module to category. And then there is the second part, which does depend explicitly on this module to category. And this is really this part dictates how the operator actually acts on your degrees of freedom. So how does it look like? Well, the way we construct this is very much the same way you build a lattice Hamilton realization of a topological field theory by using the corresponding state-sum invariant. So the way to think of a diagram like this, you want to think of it as this is an operator that acts on a neighborhood of a vertex on the triangular lattice. So a neighborhood looks like an hexagonal neighborhood. And you want to think of the degrees of freedom at the bottom as sort of being the input, and the ones at the top as being the output. So the degrees of freedom at the top are the ones that this is the result of acting with this operator. So more concretely, we have this complex. We label the edges of this complex by a gauge field, group elements in the group. And these have to satisfy a gauge field constraint. So they have to, the product of the group variables around every triangle has to be the identity. So here I put one example with G1, G2. This one has to be G1, G2 minus 1. We have to product to be the identity. And we also have degrees of freedom at the vertices. And this corresponds to object in the module to category. And they also have to satisfy some constraint. They have to be related. So given an edge, this module degrees of freedom has to be related by the action of the group variable on the corresponding edge. So it's just the assignment of degrees of freedom. And this assignment of degrees of freedom, which they need to satisfy some constraints, essentially tells you how this operator acts. Indeed, if you think of this is, you have a state that is labeled by this M1 object. When this operator acts, it acts by giving the object G acting on M1. Similarly, if you have a state labeled by G2, so this is what is represented by these equations here, the result of this action is the result is a state that is labeled by G times G2. So that's the actual action on the degrees of freedom. There is in addition some additional phase factors, which are some categorical data, which enters the definition of the module to category. So concretely, let's make there are two canonical choices of boundary conditions or module to categories we can make. So if, for instance, we choose the Dirichlet boundary condition, so the module to category over itself, what it means is that the vertex degrees of freedom are also group variables. And in that case, what it means is that if you pick, once you make a choice of degrees of freedom at the vertices, the constraint that we have for every edge basically fully dictate what must be the degrees of freedom on the edges. So what it means is that you don't have independent degrees of freedom on the edges, so you can forget about them. So you have basically a model that has only degrees of freedom at the vertices. And this corresponds to, if you want, to a pure matter theory. On the other hand, if you choose, so the choice of boundary condition with respect to the full subgroup over itself, then the module, basically the module to category is trivial. There is no non-trivial object in it. So there are no degrees of freedom at the vertices. You only have degrees of freedom at the edges. And that would be a pure gauge theory. And even more concretely, if you were to choose these coefficients here to be 1 everywhere, the resulting model they would get would be the lattice Hamilton realization of digraph-Witten theory. So essentially, when you make now a different choice of boundary condition that would be in between these two extreme cases, where you get something with degrees of freedom both on the vertices, both on the edges, and you can, this is something we do in the paper, you can demonstrate explicitly that this is the same thing as gauging the symmetry associated with the choice of subgroup that enter the definition of this module to category. So that gives us a nice way of parameterizing arbitrary models that have symmetries of various types. And actually, also this parameterization makes it convenient for us to prove in general what are the symmetry structures of these Hamiltonians. And I'm not going to go into detail, but I mentioned that the resulting symmetry structures are associated with these Morita dual categories. And there is some data that enters these computations. And we can translate this data into lattice operators and then explicitly check that these lattice operators commute with the generic Hamiltonians of this type. Okay. So one particularly interesting example is the case where this is the case we saw for Ising already, is the case where you gauge everything. So when you gauge the whole symmetry, it amounts to choosing this module to category to be kind of the trivial one, which is just too vague. And then the corresponding Morita dual, which is again the resulting symmetry structure, is referred to as the fusion to category of two representations of the group. And so I want to use this example to say a few words about two representations, because these are the examples I'm going to present next. They rely on this notion of two representation. So to understand two representation, first, it's convenient to think of group representation to invoke the equivalence between group representation and modules over the group algebra. So briefly, how does it look like? A group algebra, what it is as a vector space. This is the states in the vector space are formal linear combinations of group variables with coefficients that are complex coefficients. Then the algebraic rule, the multiplication, is given below. And obviously, because the coefficients are complex numbers, it's associative. Doesn't matter in which order you do the multiplication. Now, in that context, a module, what it is, in particular, you can think of, let's say you have a representation. What is the corresponding module of the group algebra? Where you have the vector space, and then you have an action of the group algebra on this vector space. And there is a way to do this equivalence follows from the fact that you can explicitly write down this action by using the representation, the corresponding representation. And then again, because everything is with complex numbers, we have a strict associativity, which means that it doesn't matter in which order you do. Well, it doesn't matter if you first multiply A and B and then act on a vector, or act successively with A and B. And this is just the defining property of being a representation. Now, with this in mind, what is a group 2 representation? But one way to think about it is as follows. The idea is that a group 2 representation is a categorification of the notion of group representation. And in order to talk about this, we first need to understand what is a categorification of a group algebra. So categorification, loosely speaking, the idea when you hear about categorification is that you want to turn equalities into isomorphisms. And specifically here, the goal would be to say, what if we don't want to have a strict associativity, but we want something that is weakly associative? We just want the multiplication to be associative up to an isomorphism. And similarly for the modules, we would like this module associativity we would like to weaken it. Now, you cannot do it if you have sort of complex numbers. Like if you at the end of the day, it boils down to multiplication of complex numbers, there is no way you can weaken the associativity, because complex numbers, just the multiplication, it has to be associative. So the trick is basically to define, if you want, an algebra in the same spirit, but not the coefficients. So we have still formal linear combinations of group variables, but the coefficients now are vector spaces. And vector spaces, now these are not strictly associative. So we can write a multiplication which now relies on the tensor product of vector spaces. And the tensor product of vector spaces is not quite associative, and you have to do typically a change of basis to go from one configuration to the other. And so this accomplishes what we wanted. Now, with this in mind, a module category over such a sort of group 2 algebra, if you want, is in the same spirit. It's going to be it's a category which is acted upon by G. So there is an action essentially of this group 2 algebra. At the end of the day, it's just an action of G on this category. And in the same spirit, now we have this sort of defining property of representation or of modules of a group algebra is now satisfied up to an isomorphism. And this module categories, we understand the classification really well, and similarly to the gap boundary conditions I mentioned before, these are classified by some subgroups and now some 2 cohomology class. Okay, so let me now go through several examples, and I'm going to start with an example that is very similar to the one we saw at the very beginning. So what it is, this example, it's basically the Z2 Ising model. So it's exactly the same as before, essentially, but now you have sort of 2 flavors of Z2 degrees of freedom at every vertex. We have essentially 2 copies, if you want, of the same model. So I'm not going to go through the analysis we did before, because many results just follow from what we did in the usual Ising model. In particular, you can gauge it in exactly the same way, and you get 2 copies of the model that we had we found before in the case of the Ising model. But I want to emphasize that because now we have Z2 degrees of freedom, we have a new type of surface operators that we didn't have in the case of the Ising model. And the reason why is because you can trace it back to the fact that there was a non-trivial 2 cycle, a Z2 2 cycle. So how does this operator look like? Well, it's quite easy. It just multiplies the state by a phase. And this phase is the evaluation of the 2 cycle on every triangle. So for every triangle, you evaluate the 2 cycle for the corresponding the gauge field configuration. And this 2 cycle has a simple expression in that case. -1, so G1 is the first G2 component and G2 is the second G2 component. And this commutes with the Hamiltonian. Let me do this graphically. So the way you can see that it commutes is as follows. So here, this is a graphical representation of the operator I just talked about. So for every triangle, you have this phase factor, which involves the first Z2 component of one value of the gauge field on an edge, and the second Z2 component of the gauge field on a different edge. So for every triangle, we have such phase factor. And what happens is that when you act with the Hamiltonian, in particular here with this operator, Pauli-X operators that act on the surrounding of a vertex, well, what you can see is that you pick up in the process some phase factors in principle that correspond to the action of these Pauli-Z operators. But this it follows from the fact that we have a gauge field that this for every contractible cycle, every loop of sigma z's will always be 1, and therefore it commutes. Now, something interesting is that we can define these operators on an open support, and the way it works is as follows: is that you apply, so you multiply by this phase factor. So let's say here the gray area represent this surface operator I just talked about, and the white area will be the trivial operator. I'm saying that it is possible to define it on an open support like that, but there is a caveat: is that if you don't do really, if you really just restrict the definition of your surface operator to this gray area, and you check the commutation with the Hamiltonian at the vertices that are at the boundary of this operator, then it wouldn't quite commute. You will have some spurious terms. So what you have to do is that you have to couple this operator with a line operator. So you have to put a line operator on this boundary. And this line operator is essentially a Wilson-like type object. So it's like you take the projective representation of Z2, and you evaluate it essentially on all the gauge fields on this boundary. You multiply all these matrices, and then you take the trace. And it then follows from the defining property of the projective representations that as you do a gauge transformations at this vertex, you will pick up some 2 cycles coming from the defining property of a projective representation, which will cancel the spurious phase factors that came from the surface operator in the gray area. Now, how does it fit with the sort of mathematical understanding of these operators? So the symmetry structure of this model is a 2-rep of Z2. The objects are module categories over Z2. And the line operators are maps between module categories. So this is what we call the module functors. And in particular, we know that the category of lines between, so the this operator I've been talking about and the trivial one, is equivalent to the category of projective representation of Z2, which is precisely why we were able to define this operator on an open support by coupling it with this operator I defined in terms of the projective representations. Okay, so now I want to finish by going through a series of examples where we're going to discuss the same model. So it's going to be an Ising-like model, but this time with the input will be a non-abelian group. Starting, so even though we start from the simplest non-abelian group, which is S3, what is interesting is that there are several gauging we can do. and we're going to study the resulting symmetry structures. So first, I need a bit of I need to set some notations. The point is the point of this notation will be to write down the operators as explicitly as possible on the lattice. And so in particular, what we want to exploit is the fact that the group S3 of order 6 can be thought as the summa direct product of Z2 acting on Z3 via the action of Z2 on Z3 by automorphism. And that what it means that you can write down the group elements in S3, you can decompose them into a Z2 part and a Z3 part, and you can write down the multiplication explicitly using this decomposition. And what is interesting is that you see here this phi Q1, this is basically the action of Z2 on Z3. Okay, so correspondingly, I need some basic operators. So we already know the Pauli operators that we've been using in the case of the Ising model. That's basically for the Z2 part of the Hamiltonian. And then I need the Z3 equivalent. So we have the sigma X and sigma Z operators. These are the equivalent of the Pauli matrices for Z3. And we have this matrix gamma. It will show up in a couple of places. Gamma essentially translates the fact that there is an action of Z2 on Z3. So every time there is, it will show up, it's because implicitly we are using the action of Z2 on Z3. So using this, I can write down explicitly what an S3 transverse field Ising model look like. So the degrees of freedom are just this S3 mature field defined at all the vertices. And then we have two terms that are the analogs of what we had for the Ising model. So we have a term that sort of forces the endpoint, the matter degrees of freedom at the endpoints of the edge to be aligned, to be labeled by the same group element, which you can write down explicitly in terms of the operators I just introduced. And we have the equivalent of the transverse field, which is given in terms of the action of the group S3. So here it would be the left action. Now, for what we need, it is enough to look at specifically the action of this operator when G corresponds to a generator of S3. So these generators are R and S. So these operators act by left multiplication by R and S. And we can write this operation of acting by left multiplication with the corresponding group elements explicitly in terms of the operators I just introduced. So here, for instance, you have the sigma X act on the Z2 part, the gamma act on the Z3 part, and together this amounts to changing the state by left multiplication by R. And I'm representing this graphically like this. I'm just summarizing these operators. This is really the non-trivial part of the Hamiltonian we will have to worry about. So I'm summarizing how it looks like for the generators. Now we can gauge the whole group. And this is something that we've done before in the case of Z2. And we get something very similar. We have now a pure gauge theory with degrees of freedom just on the edges. And again, we can write down explicitly the resulting Hamiltonian in terms of the operators I just introduced. So first we have a term that forces the group elements on the edges to be the identity. And then we have a term that essentially implements some gauge transformation around the vertex. And this gauge transformation, the actual specific definitions doesn't really matter. Just want to emphasize that, again, we can write it down explicitly in terms of Z2 and Z3 operators. And the fact that here you see two different operators for a given types of operators for a given A operator is because since it's non-abelian, now we have to define some orientation on the edges. And depending if an edge is outgoing or ingoing, you're going to have to act with left or right multiplication, which explains why we always have these two flavors of operators. Let me also mention that I introduced a new notation here. These operators there, what they do, these operators, is that they act both on the Z2 and Z3 degrees of freedom, or specifically, these correspond to operators that act on the Z3 degrees of freedom by sigma X, controlled by the value of the Z2 gauge field. So the action actually depends on whether the value is 0 or 1 for the Z2 component. And this satisfies computational relations that I'm going to use in a second, that if you act with the Pauli X on the Z2 part, then it sort of transforms, it gives you the adjoint of the operator acting on the Z3 part. Now we can also gauge, so then this...
Excuse me, yeah, I have a question here.
Sure.
So looks like these two operator is defined on the small loop around the vertex in two-dimensional lattice. That's a space. That's my understanding. So can you define this operator in a large loop with arbitrary shape? Or you just compose those small loop operator, you can get a large loop operator? Because of the higher symmetry or something, they are kind of transformation on arbitrary loops.
Yeah, I mean, so here it's really, I mean, I'm choosing to define the Hamiltonian like this, right? So in that case, the idea is because we want these operators to implement some kind of local, like a gauge transformation, right? This would be like, if you forget about the first term in the Hamiltonian, this is just a quantum double model, right? It's the quantum double for the S3 group, right? So I could define a Hamiltonian that is less local, with like an action of that acts on there, like corresponding to a larger loop. But here it's really a choice I make. I'm deciding that's the Hamiltonian I want to consider, right?
Yeah, but my question is, when you consider symmetry transformation, the symmetry transformation can be defined on arbitrary loops. So yes, whether there's a similar construction like this for the symmetry transformation on arbitrary loop.
So I'm gonna show the symmetries after. So right now I'm listing the Hamiltonians, and then I will go through the symmetries. Yeah, sure. I should have said that at the beginning. Yeah. So now what if I'm gauging Z3? So now again, so the way we do it here, I'm just giving you the results. Actually, the way we found these Hamiltonians, so gauging Z3 is actually still kind of manageable in the canonical way. When you start gauging Z2, which is a non-normal subgroup, then it's not so easy to do it following the canonical approach. But the way we did it is really by applying our program using this way of writing Hamiltonians in terms of module to categories, and then it just spits out the Hamiltonians I'm giving you here. So that's why I'm just giving them like this. So how does it work when you gauge Z3? Well, gauge Z3 means essentially you leave the Z2 matter degrees of freedom at the vertices untouched, but now you have a Z3 gauge field at the edges. And what we have, again, we have two types of Hamiltonians, but now they are a bit different because we have degrees of freedom at both vertices and edges. We have first a term that sort of projects everything to be either the same or the identity, so it's not particularly interesting. But we have also these vertex terms. And these vertex terms, what is interesting is that some of them, they mix these degrees of freedom. So here, what is the meaning of the second operator? It's the statement that you act with sigma x operator on the Z3 degrees of freedom or the adjoint, depending on the value of the matter field at the vertex. And the fact that you have this dependency, it's reminiscent of the fact that you have this Z2, you started from a group that you have an action of Z2 on Z3. Now the last model, which is gauging Z2, which is in the way, as I said, the most exotic one because it amounts to gauging a non-normal subgroup, which is always a bit peculiar. But what we have, the recipe is still the same. We are left with a Z2, so Z3 vector degrees of freedom, a Z2 gauge field, okay? We have a first term of the Hamiltonian, which is always of the same flavor. And then the second one, so we have, you see, like this operator, we act with the sigma x on the Z3 degrees of freedom at the vertices. And then we have the second operator, which again mixes both Z2 and Z3 degrees of freedom. It acts on both types of degrees of freedom at the same time. So here is just a summary of sort of the interesting operators in these Hamiltonians, the ones that we need to worry about when we start talking about the symmetry structures. But again, the actual definition doesn't matter too much. It's more like to see the general form of these operators. So how does the symmetry look like? So obviously the initial Hamiltonian, I'm not going through it. It just has S3 symmetry, an ordinary symmetry. So let me jump straight away to the second one, the one obtained by gauging everything. So here you have, I'm just recalling the operators. So what do we have? Well, in particular, we have a one-form rep S3 symmetry. This is something that I mentioned at the beginning that we expect. And here, how does it work? Well, it's these Wilson line operators, right? You just evaluate a given representation of S3 on every edge that form a loop that can be non-contractible, right? So it can be, this loop can be as big as you want, in particular non-contractible. And this it's a one-form rep S3 symmetry. And the fact that this comes with the Hamiltonian, so you can check it explicitly. or you can just rely on the fact that Wilson operators are gauge invariant. And these operators over here, they basically generate a gauge transformations, and therefore you know that it will commute with the Hamiltonian. And we have also non-invertible surface operators. In that case, we have several. We have one that looks very much like the one we had in the Z2 case, where it acts via this, you assign these virtual degrees of freedom, and then you have these constraints between these virtual degrees of freedom and the gauge field. And in fine, it just projects onto the singlet sector of the one-form symmetry. But you can also find some that are with respect to essentially a different type of subgroup. And these are of the same flavor, but a little bit more exotic, because you have to take into account the fact that you have this action of Z2 and Z3. But at the end of the day, the effect is of a similar flavor. It's going to project onto some singlet sector, but with respect to some subsymmetry of the one-form symmetry. So this is just to highlight some of the features of this model. Again, similarly to what we did for Ising, we can look at the line operators and everything, and then we can check that all this together, it reproduces, it organizes into this fusion to category of two representation of the group. Now about the model obtained by gauging Z3. We have Z3 degrees of freedom on the edges, Z2 degrees of freedom at the vertices. Again, I'm just going to highlight some of the most interesting features. And one of them is the zero form Z2 symmetry. And here, maybe I have to be slightly careful with this terminology, because this is not an ordinary Z2 symmetry. So why is that? So a naive guess for what would be the Z2 symmetry would be to act with Pauli X operators at the vertices. But then it wouldn't commute with the term over here, the term on the right. Why is that? Well, because of the commutation relation I wrote here, is that if you act with the Pauli X on the vertex degrees of freedom here, it will flip the degrees of freedom acting on the surrounding edges. So it wouldn't actually commute with it. So what you have to do is that you have to couple it. You have to couple this operator with these gamma matrices. The reason why, because the role of these gamma matrices is basically to perform charge conjugation. So when you couple the two effects cancel, and then this is actually a Z2 symmetry. The one form, you have a one form Z3 symmetry, which is in that case conventional. Just if you take any loop, contractible or non-contractible, and you act with the sigma Z operators on them, it will commute with the Hamiltonian. Again, it's just if you're on the gauge invariance, it follows on the gauge invariance of Wilson lines. And they do not actually quite commute with one another. And why is that? Is because of these gammas that we have in the Z2 part. The gammas, they will also act on this sigma Z. And therefore, we have an action of the zero form operator, or the surface operators, on these line operators. And this is exactly the kind of two-group structure that we expect. We have what we call a two-group symmetry, or more specifically, by including all the lines and everything, what you can show is that these symmetry operators are organized into the fusion to category of two-group graded two vector spaces, which is notated at the bottom. So finally, now when we gauge the non-normal subgroup, Z2, this is where we get the most exotic type of symmetries. Even though the Hamiltonians look it doesn't look that bad. And in particular, we have some non-invertible surface operators that are interesting. So to understand these surface operators, first you could ask, okay, is there a Z3 zero form? Is there a conventional Z3 zero form? And in that case, the guess would be to just act with sigma X operators on all the vertices. But this wouldn't commute with the Hamiltonian. The reason why is because of these gammas over there. Because of the gammas on this, when you do the commutation, it would change your operator from sigma X to sigma X dagger, and therefore it cannot be a symmetry. It turns out that the way to fix it, the proper way to fix that, in such a way that you actually end up with a simple surface operator, is to couple this sort of naive guess with a non-invertible surface operator, one of these condensation defect operator. And the way we define them, so we have this condensation defect operator with respect to Z2. So we have this virtual Z2 degrees of freedom at the vertices that whose effect is the same as before, then like to project onto some singlet sector. But the key is that depending on the value of these virtual degrees of freedom, then you will act with either with sigma x or with sigma x dagger. This is the meaning of this equation here. Phi is the action on, it's just a way of writing what I just said, is the fact that depending on the value of these virtual degrees of freedom, you will act with sigma x or sigma x dagger. So how does that, let me try to motivate this a bit. So what happens when you, so this in the middle, this represents essentially our symmetry operator locally, how it looks like. And then we act, what happens when we act with the Hamiltonian. So the action, something we saw before, is that if you act with sigma x, then it shifts the gauge field by 1, which means that to find a configuration of virtual degrees of freedom that work, you have to shift the one at the vertex by 1 as well. So this is the meaning of the equation at the right. At the same time, you're acting with gamma on sigma x, which means that it's actually sigma x dagger or sigma x to the -1. And so you're changing this part of the operator with the -1. Now, when you do your change of summation variable, when you redefine n to be n plus 1 to be n, you shift here, you get n plus 1. And this operation amounts to flipping the sign over there and therefore to recover the initial operator. So this is exactly the coupling with this non-invertible defect is exactly what then will make it, will make the sort of the naive Z3 zero form operator actually commute with the Hamiltonian. So this is one, so this is the one I just presented. This is one operator. There is also obviously one that amounts to just the pure condensation defect and the pure non-invertible operator without this reaction. And also there was another one you can define, which is equivalent to the previous one, but where you actually act with sort of, instead of acting with sigma x and sigma x dagger, you act with sigma x dagger and sigma x. And then the fusion rules, you can compute the fusion rules on the lattice and using this kind of formulas that we have, these lattice formulas that we have, you can explicitly check the fusion rules by relying on the similarly to the way we did it for Ising model, but taking into account the specificities of this model. And you have these funny fusion rules where if you multiply these two operators that are the same, you're getting actually the pure non-invertible part, and then this other one over there. And all these operators and the way they are defined, the fact that we have to couple this naive Z3 zero form operator to this non-invertible condensation defect, this is something that we also see on the category theoretic side, and we can match all these constructions to this purely formal object, which is the fusion to category of two representations of the two groups.
Yeah, Kirsten, I have a question here.
Yeah.
For the fusion rule, when you have this circle with a dot in the middle and also square with a plus in the middle, can they be interpreted as an operator product because those operators are defined? Or maybe there's there's some difference.
So let me clarify the notation. So here I'm using this point dot because, so by that I mean the monoidal structure, because these objects, these operators correspond to objects in this fusion to categories. So by this notation, I'm really referring to the monoidal structure in this category. And then the reason I'm using this plus is, so it comes from the linear structure of this fusion to category. It has to do with the fact that, so these operators, as I said, correspond to objects in 2-rep of the 2 group. Objects in the 2-rep of the 2 group are in particular categories. They are module categories, but they are in particular categories. And so this plus is essentially, if you want, the linear structure. It's like it corresponds to this the addition, if you want, of categories. So that's why I'm using this symbol.
So they're really the relation in category.
Yeah.
But then my question is, can you compute those relations in category from this explicit operator when you can multiply them? You can add them. That becomes some kind of linear algebra relation. Whether, from this linear algebra relation operator, can you compute this categorical relation?
Yeah, I mean, so this we can really compute explicitly because at the end of the day, this basically gives you So here, first of all, I should clarify that I'm always working implicitly on the torus. If you're working on a different topology, you have the fusion coefficients are different. You have this, we said that the fusion coefficients are TQFTs themselves, so they actually depend on the underlying topology. And then at the end of the day, these are really sort of numbers, like they amount to coupling with the phase, and then they give you, at the end of the day, this structure will translate in an actual addition at the level of the values of the corresponding TQFTs, right? So it's not just sort of formal. Now we actually see this decomposition explicitly. Yeah.
Okay.
So that was the last
related question.
Yeah.
So how correct or wrong is it to think of your circle and your plus as tensor product and direct product?
So I specifically didn't want to use tensor product because this would imply that these guys are somehow associated to representations of a group when they're actually two representations. So it's really more like what it is actually, this is like you take the Delin tensor product of the corresponding categories. These define, you can then define a module structure on the result of this Delin tensor product, and then you decompose the resulting module to categories into simple indecomposable module categories. So we are really using the linear structure of sort of two vector spaces, which are a special kind of categories, and the Delin tensor product coupled with the action of the group on it. Yeah. It is reminiscent, of course, of the tensor product, because tensor product of representation is similar. You take the tensor product of the vector spaces, you act simultaneously on them with the group, and then you decompose, right? But this is a categorification of this. Yeah.
Thank you.
So that was it. So let me just list a couple of questions which I think are interesting. So now we have either in the lattice or in the continuum, I mean, we have a pretty good understanding of these higher categorical symmetries, and in particular how they emerge. And I think it's very interesting to study what are the physical implications of these symmetries, and in particular to which extent having these symmetries, how does it, how can you exploit maybe the fact that we have new types of symmetries to reduce the number of degrees of freedom in a way, if you want to do like numerical simulations, and so on and so forth. I mean, basically the things that we usually do with ordinary symmetries. Something that is particularly interesting, and actually we have a very good understanding of how to do that in 1+1 dimension in a similar language. And so I think we can also do something similar in 2+1 dimension, is to study the superselection sectors of these models. So that is studying the symmetry twisted boundary conditions of these two-dimensional models, and then what are the charge sectors with respect to the symmetries. And in particular, something that is interesting is to think of what it means to have symmetry twisted boundary conditions with respect to these non-invertible condensation defect operators. Another interesting question is to investigate self-dual models in 2+1 dimensions. So in that case, self-dual, you could, with respect to a gauging procedure, for instance. And the reason why I think it's interesting is because it's much more difficult to find self-dual models in 2+1 dimension, precisely because when you start gauging, you're changing the symmetry structure. So finding something that is invariant, which will in particular preserve the symmetry structure, it's going to be either very boring or probably very complicated. So this is interesting to find examples along these lines. And also, so there has been very recently some studies already of studying the operators that are charged under this, so the type of higher categorical symmetry that described in this paper. And it would be interesting to realize them. So we already have some examples, but to realize all of them on the lattice in the same spirit of the way we studied the symmetry operators. And that's it, and thank you for your attention.
Thanks, Clement, for a very nice talk. So if there are any questions, please feel free to directly ask, unmute yourself.
Yeah, I have a question about this first example, this Z2 symmetry. And you mentioned that there's a non-invertible symmetry related to this condensation defect.
Yeah.
What is their charge? I'm trying to see. I couldn't imagine what is their charge.
So you're asking for the charge objects with respect to
the charge
symmetry?
of. So this operator are kind of one-dimensional.
Well, they are two-dimensional. So they are like surface operators, but indeed you can realize them as by thinking of a network of lines, right? By summing all possible possible line configurations. So the charge.
When I say one-dimensional, really in space it's one-dimensional. It's like a string operator. In a Hamiltonian setting.
Collectively, once you. So if you take a patch and then you sum over all possible lines within that patch, then effectively we think of the result as a surface operator. Even though it's constituted of lines, we think of it as a surface operator. But indeed, then I guess, so I haven't actually...
Well, it is a surface operator, right? You take into the identity
it's a surface in space-time,
and then you put lines on top of it. So it is a surface, right?
Yeah, not just in space-time. It's in space, it's also a surface already. So here, maybe
space, and so that's really this is like the language. So the surface operator, I think you mean is in space time is a surface.
No. It's actually a surface in space.
It's the operator acting. So the surface operator acting on the space. I see.
So really, you think like you have, let's say, a torus, and then you're inserting. You sum over all possible insertions of Z2 lines on it. So basically, every possible loop, you put Pauli's like along every possible loop, and you sum over all possible configurations of these operators. So effectively, it acts on the whole system at once, and it actually, this is why, and the result is that it projects onto the singlet sector. So it's actually the action is non-local, because at the end of the day, it projects onto the singlet sector with respect to the one-form symmetry.
Thanks. Yeah, I'm confused here. So even in the Hamiltonian formulation, this is the operator act on the surface.
Yes.
Okay. And so this so therefore in this expression, sum over G, I just wonder this how should I view this?
So here, sum over G, I'm summing over one cocycles, meaning I'm summing over all possible assignments of group variables to the edges, such that they multiply to the identity for every loop, for every closed loop.
Okay.
And then this N are for every, you can think of them as, as I was saying, virtual degrees of freedom at the vertices. But this is just one way of expressing the operator that projects onto the singlet sector. You can also take this as a...
So their charge will be more like a point. If the operator acts on the surface in two-dimensional space, then their charge will be like a point, like the zero dimension, the charge object.
So I want to say,
that confuses me.
I want to say yes, but I haven't really actually thought about what the charged operators would look like for these symmetry operators. So in the same spirit that the symmetry operators descend from the one-form symmetry, the charges of the corresponding operators I expect will also sort of descend from the charges of the one-form symmetry, but I'm not actually sure how they would look like. I mean, maybe people in the audience have some insight on this.
If I can add a comment, I think there are no non-trivial operators that transform under this operator. So you don't actually get any new charges. The only charges are the ones that you already had for.
Yeah, so I guess it's going to be a network of the ones that are for the one-form symmetry or something.
Yes.
Yeah.
But there might be non-trivial local operators for other gaugings of subgroups of non-abelian zero-form symmetries in 2D. So the non-invertible surface operators that one gets by gauging subgroups of say S3 or some other group, there might be local operators charged under those.
Yeah, maybe.
So even though there are no local operators charged under a condensation surface operator, there are line operators, 0 plus one-dimensional line operators that can be charged. And of condensation surface operator.
Yeah, makes sense.
Thanks. Yeah.
So I think there are some hands raised. Nat, please go ahead.
I wanted to ask about the case for S3 where you gauge the non-normal subgroup.
Yeah.
So there you have a Z3 zero-form symmetry, and somehow should I think of it as enriching the Z2 like topological order in some way? Or?
So the thing is that what's important to keep in mind is that you cannot define the Z3 zero form on its own. Like you cannot just so this would amount to just multiply with these sigma x operators. Mm-hmm. You cannot just do it on it. It's not possible if you don't combine it with these non-invertible operators. I feel like if you think in terms of enrich, it sort of suggests that you would be able to maybe define it on its own. Mm-hmm. And at the sort of algebraically at the category theoretic level, you sort of, I mean, you see it immediately, like what labels this Z3 part. You see that you cannot find an object that is only labeled by that. It's only possible to have something labeled by a character of Z3 if you couple it with what labels these non-invertible surface operators. So it's quite exotic in that mm-hmm. In that sense, yeah.
And so at this point, is it still invertible?
It's not invertible. No,
it is not invertible.
It's not invertible. Yeah. So the fusion rules are of this type. It is not possible to have. You really cannot have operators whose fusion rules are just given by Z3 multiplication. You don't have that in this model. Yeah.
I see. Okay. Thank you.
There's another hand raised. Orko, if you
Yeah, thanks. Thanks for a nice talk. I had a question about your invertible twist defect. I think it was in the Z2 times Z2 case. So should I think of this as some kind of SPT phase sitting on some patch?
Yeah. It's basically it's like pasting if you want an SPT in a way. So these symmetries were referred to. So the papers I'm referring to here, these were referred to as dynamical symmetries by Fuchs and Schweigert and others. But yeah, at the end of the day, it's very much something on that flavor. It's like you're pasting an SPT on top of the model, which is why it's invertible, because the SPT is invertible as a TQFT.
I see. So then the other non-invertible surface operators, should I think of them as some kind of symmetry breaking states that I'm pasting on? 1 + 1 symmetry breaking states I'm pasting on.
I'm a bit more tempted to think of them as actually coupling them with like a topological model. Like for instance, in the case of Z2, the non-divertible operator, it sort of amounts to coupling with a pure Z2 gauge theory, right? So a topological gauge theory rather than a symmetry breaking model, which are then they are non-invertible.
Actually, you can also think of them as symmetry breaking.
Can I just intersect here, because I mean this may not be clear from the way you presented this, but you can reconstruct all of these, 2-rep G and also all the partial things using precisely this picture that you're stacking with some particular GT QFTs. This is basically an equivalent way of doing this rather than just doing 2-rep.
Indeed,
so what you're asking is exactly one other natural way of actually constructing these lines.
Indeed, yes. Thank you.
And it was done in some papers. So.
I know what you're referring to. Yeah.
So the Z2 gauge theory actually is like a Z2 spontaneous symmetry broken phase in 2D.
I see. So in general, these surface operators, should I think of them as lower dimensional phases? So in 3 + 1D, I could do
so this is exactly, I think, the statement that Sakura was making. This is another way of thinking about it like this, indeed. Yeah.
I see. Okay. Thank you so much. Yeah.
Are there any other questions? If not, then let's thank Clement again, and we can.
Thank you very much. Yeah.
Thank you.
We can stop recording.